Hello everyone, welcome to ARM through C, where we learn the assembly language by decompiling C code. Last time I sort of promised you that we were going to talk about functions in assembly. Well, functions in assembly don't exist, so see you next time. Wait, hold on, don't go just yet. While it is absolutely true that functions don't exist in assembly per se, they allow for the concept of functions if you follow certain conventions. Let me show you that by decompiling some C code. But before we really start analyzing line by line the assembly code generated by the compiler, I would like to take a detour and make an introduction to the memory management techniques that will be used for functional programming. When I started programming, I was aware of the notions of the heap and the stack. Well, we won't touch the heap in this case. We'll talk only about the stack. And I knew approximately what the stack is, but I didn't really know where it came from. I mean, why such a method of managing memory? So I was thinking of maybe introducing a few alternatives to memory management in the context of functions, and then see why stack is such a useful and almost natural concept of memory management within a computer in general. In fact, it seems that it's so natural and so fundamental that it appears at least as early as 1947, as it is mentioned by Turing in a lecture when he basically speaks about the stack, but he doesn't call the operations that we know today, like push and pop, that we'll see later on. He uses bury and unbury, but he's definitely talking and using the same principle. But when I was first introduced to the concept of the stack, it wasn't clear at all why it would be so optimal memory management technique. It just seemed overly complicated. So maybe as an introduction before jumping into the code, I was thinking of giving what could be an alternative to the stack, and then see its drawbacks, and then really understand why the stack is the ultimate solution. And consequently, this will maybe make going through the code a bit easier, understanding the real reasoning behind the stack. But even before that, another small tangent. Why functions? Why functional programming? Let's keep it brief. Functions are kind to the human reasoning because they let you dissect a problem into smaller problems that you can keep in your head. So it's kind of natural to divide a problem in smaller pieces and then also reuse those pieces in multiple situations. So functions are useful. Let's do functions. The spread. I'll present here the spread memory allocation scheme that will make introduction to the stack a bit easier by seeing its drawbacks. And I have this little piece of code to help with the explanation. In this program, we have a main function which calls an area function that calculates an area of a rectangle. But within that area function, we call another convert units function, which converts the units from meters to centimeters. So we have a call within a call. Now, to make the functions come alive in assembly, we have to solve a few problems. First problem is the fact that we don't have the notion of parameters in assembly. But we can circumvent this problem by adopting a convention. You could say, for instance, that before calling a function, we will put its parameters into registers from R0 to R4. And when the function will be called, it will just expect by convention that the parameters are there. And when it will exit, it will save the result in one of those agreed upon registers. In this naive scheme, we would have the function placed in flash one after the other, and we would use the branch instruction to get in and out of the functions. Whereas for the RAM part, we'd have all the internal variables of each function clearly separated in different regions. That way there would be no overlap and no one would be stepping on each other's toes. The drawback is that we are using the memory of all the functions all the time, even though there's only one function active in each moment. Let's step through. We first set the values for height and width into the registers, and then with the help of RAM, if there are some other operations in there, we set the registers R0 and R1 as parameters. We then jump to the area function, where again we set its parameters to call the convert unit function. We then call we branch to the convert units function, where we finally calculate the new units. Just ignore the set parameters step because it's a mistake. So we finally calculate the new units. We pass the value to the caller, which is the area function. We return to the area. The area knows where to expect the result. It takes the result and it does its calculation, calculates the area, and returns to main. This is a very naive approach, and you can spot the error right away. The problem is that you cannot let the callee function know where to jump after it's finished, because the called function can be called from various different functions, or as it's in our case, it's called twice in the area function. So it returns to it should return to two different points, but it doesn't. So we have to do better. A better scheme would be to have a return address saved somewhere before we call the function. And the callee function would know where to find that address by convention, but this is not the ARM procedure call standard convention, it's just something I'm making up. It would use that address to jump to the correct location. This way we would avoid the problems in the last example. I've decided to keep the length of the videos around 10 minutes, so I'm making this a two-part episode. I hope we've already covered something. We covered the ARM procedure call standard, that it's used in real life, that the C compiler uses it. We've discovered that there has to be a way for the called function to jump back to where it was called, one step later. And we kind of solved that problem, but in reality it's solved much better. And in that regard, next time we'll introduce the program counter and the link register that help with that. We've seen a primitive attempt at managing memory, that is making sure that we don't overwrite stuff with one function that already belongs to another function and mess up the result. And we solved it by totally separating the area that the function uses. But there's a much better way that always keeps track of only that is necessary, and that is the stack. And next time, I promise, we'll jump into the code and see how it's really done. And we'll introduce two more registers, the stack pointer and the frame pointer, that keep track of where in RAM can we write data.